In this video, I am discussing quite a different problem on Laplace equation. Here, a potential field V is given, which is equal to some constant divided by a variable. That is V equal to C1 by R. It is given that C1 is an arbitrary constant. Now we have to find out the particular coordinate system in which this Laplace equation is satisfied. That means we have to find out in which coordinate system this potential field satisfies Laplace equation. You know that Laplace equation is given by del square V equal to 0. Considering V equal to C1 by R as a potential field, we have to verify in which coordinate system the Laplace equation is satisfied. Then the question comes what R is. R can be any of the three variables of a particular coordinate system. Let us start our discussion with rectangular coordinate system. In rectangular coordinate system, we have three variables. They are x, y, and z. So here, your R can be either x or y or z. Let us start our discussion with R equal to x. This is going to be our first part of the solution. And later, I'm going to take R as y and later z. Then we have to verify the Laplace equation del square V equal to 0. Okay then. We shall take now the Laplace equation. After substituting this V, we have to check whether the solution is 0 or not. So we shall not take 0 now itself. We shall start with del square V. The expansion for del square V is dou square by dou x square, dou square V by dou y square, and dou square V by dou z square. If you observe carefully, all the three terms, that is double differentiation of potential V with respect to x, y, z, are similar. Dou square V by dou x square is similar to dou square V by dou y square. That means if you verify for R equal to x, it is as good as verifying for R equal to y and also z. So any one verification is enough here. Then we shall continue with our assumption. Since V is a function of that is R, nothing but x only. Del square V becomes d square V by dx square. So the two terms are not taken here. They are going to be 0. Now, let us verify del square V for the given potential field, that is C1 by R, nothing but C1 by X in this part. So now one differentiation will do here. C1 is constant. Differentiation of 1 by x is minus 1 by x square. Now we'll go for one more differentiation. Let us take minus C1 out. 1 by x square differentiation is minus 2 by x cube. Finally, we get 2c1 by x cube. And please note, this is not equal to 0. That means by taking r equal to x, you can prove that del square v is not equal to 0. Similarly, if we try other possibilities in this coordinate system, we may end up with y cube, which is also not equal to 0. And with z also will not be equal to 0. So that means conclusion. Therefore, the potential function v equal to c1 by r doesn't satisfy Laplace equation. In rectangular coordinate system or Cartesian coordinate system. So now let us verify the same way the cylindrical coordinate system. Step 2, in cylindrical coordinate system, the variables are, as you all know, it is rho, phi, z. And the expansion for del square v is equal to 1 by rho, dou by dou rho into dou v by dou rho. The first term of the expansion, second term is 1 by rho square, dou square v by dou phi square, plus dou square v by dou z square. So here, dou square v by dou z square term is similar to the expansion in rectangular coordinate system. In RCS also we find the same kind of equation. So we cannot satisfy if R is Z. So we can conclude that one. If R equal to Z, what happens to our V? Sorry, del square V. Our del square V would be same as the previous value. That is going to be 2c1 by z cube, which is not equal to 0. From the part 1. This is from the part 1. So we rule out R being equal to Z. Now we shall go with rho. Let the variable R equal to rho. Then what happens? Del square V rho only. 1 by rho d by d rho into dv by d rho. See this condition now. Now let us see what happens if we substitute for v d by d rho. Let us say that equation given in the problem is C1 by R. R is nothing but rho only. That is, here V becomes C1 by rho. Now we have to check for the value of del square V. 1 by rho. Differentiate here. C1 is constant. 1 by rho differentiation is minus 1 by rho square. One more step we can write here itself. D by d rho. So what happens here? It's going to be minus C1. One rho cancelled, so divided by rho again. Now what happens? See, 1 by rho. Again minus C1 constant. Differentiation of 1 by rho is minus 1 by rho square. So finally, this becomes C1 by rho cube. So this is also not equal to 0. So we verified for two variables in cylindrical coordinate system. One is rho, another one is z. Let us check the another one possible, that phi. By inspection, you can say that it is also not possible, but if you want to try, if r equal to phi, then the given potential equation C1 by r becomes C1 by phi. Then our del square V is what? For phi, it's going to be 1 by rho square d square V by d phi square. This is the second term of the expansion, phi component. So with this, let us say what happens. 1 by rho square d square by d phi square. That is going to be C1 by phi. Double differentiation is already verified in the RCS itself. So based on that, we can copy the solution here. So this fellow would give us 2C1 by phi cube. This is based on the part 1. So this is also not equal to 0. So let us conclude now. Therefore, V equal to C1 by R doesn't satisfy the Laplace equation. Doesn't satisfy the Laplace equation in cylindrical coordinate system. Now we are going for the third coordinate system, spherical coordinate system. What happens in spherical? S, C, S. Which are the variables in spherical? The three variables are theta and phi. Let us go with the expansion. r theta phi. Del square V is equal to 1 by r square dou by dou r square into dou V by dou r plus 1 by r square sine theta dou by dou theta of sine theta into dou V by dou theta. The last term here is r square sine square theta dou square V by dou phi square. So this is the expansion. Let us verify the equations one by one. Let here r is equal to the radial distance r. That means our potential function V becomes C1 by small r. Then the expansion of del square V 1 by r square d by dr r square dv by dr. One by r square differentiation of r square into differentiation of V. And we know that V is C1 by R. One by R d by dr r square. Differentiate the potential equation. C1 is constant. Differentiation of 1 by r is minus 1 by r square. 1 by r square d by dr of, here what happens? The r square and r square are cancelled, and we are left with now minus C1. Next step, 1 by r square differentiation of C1 is constant, that is 0. So finally, we got a solution for this problem, that is del square V equal to 0. Therefore, V is equal to C1 by R satisfies the Laplace equation when r equal to r in spherical coordinates, r spherical coordinate system. That is the potential equation V satisfies the Laplace equation when the variable is equal to r. That is, when capital R, the variable is equal to r. R is the radial component, a radial distance. Radial distance can speak about the symmetry of potential field. That is, V possesses or exhibits radial symmetry. That means When the R value, that is small r value changes, potential P changes. So if you have a sphere of some radius, let us say R1, the potential is V1. So the sphere is an equipotential surface. V remains constant on the entire sphere or spherical surface. If we choose another sphere of radius R2, then the potential value on the sphere becomes V2. That means V changes with respect to radius. That's why all these spherical surfaces are symmetric with respect to each other or with respect to origin. Hence, we can say that the potential function exhibits radial symmetry or spherical symmetry. Spherical symmetry. If we had satisfied the Laplace equation with theta instead of r, then we would have told that the potential function satisfies the angular symmetry with respect to z-axis. We know that theta is conical angle that is defined in spherical coordinate system. The angle theta is measured with respect to z-axis, and it is a cone angle. That means this angle is also theta. Then we would have declared that V exhibits conical symmetry. That means potential V remains constant on a cone or conical surface defined at a constant angle theta. If R had satisfied the Laplace equation with the variable phi, then would have told the potential function exhibits azimuthal symmetry. So like this, depending upon the variable, we can declare the symmetry of the potential function. Here, the function exhibits spherical symmetry. Thank you.